Hi, my name is Alex Scarlatos, and I'm going to present our paper, Simulated Students and Tutoring Dialogues, Substance or Illusion. Large language models are increasingly important in education, being used as personalized tutors in systems such as Duolingo and Khan Academy, as well as mainstream LLMs such as ChatGPT and Claude. There are some early results showing that students might experience better learning outcomes when using LLMs as tutors, but these tutors are typically designed with a top-down approach using prompt engineering. The question is, can we use a data-driven approach to ensure that students always experience better learning outcomes when using these systems? A promising pathway to achieving this goal is using simulated students, i.e. large language models that role-play students in tutoring dialogues. You can imagine a reinforcement learning loop where a simulated student interacts with the simulated tutor, we measure the learning outcomes of this simulated student, and then we provide rewards and update the tutoring agent based on these measured outcomes. But there's a problem here again. What if the simulated students are not behaving like real students, i.e. realistically? We might be able to identify realism in a dialogue, but it's a little bit hard to define. Let's consider the following example where there's a math problem that a student is trying to solve by working with a tutor, and at this point in the dialogue, the student makes a simple mistake by typing 8 instead of 6. We can consider an LLM that tries to simulate this turn for the student, and this response is not very realistic because it solves the entire problem rather than only solving the partial problem posed by the tutor, and it's clearly LLM generated using the double hyphen and proper grammar compared to the student's short responses. We can look at an alternative simulated turn for the student. This looks a little bit better because it uses short mathematical text similar to the student, and it doesn't solve the entire problem and only solves the partial problem. However, this response is correct, whereas the student gave an incorrect response at this point in the dialogue, and it doesn't really reflect the student's messy behavior, which is observable based on their previous responses. In this work, we propose to systematically evaluate realism in student simulations. We do so by identifying high-level dimensions of student behavior, knowledge, and language, all grounded in the learning sciences research. We create reference-based metrics for each of these dimensions, which are grounded in real student data. The advantage of doing this is that we don't rely on predefined notions of student behavior and prompt engineering, which may or may not align with real student observations. To the best of our knowledge, our work is the first automated turn-level evaluation suite for realism in simulated students. Our first metric is dialogue acts, which measures the high-level action that a student is taking in any given turn in a dialogue. This indicates a student's behavior and learning style. We use a mixture of prompting and fine-tuned language models to label a single act for every ground truth or predicted student turn from a predefined set. We compare the labeled act of the ground truth turn and the simulated turn and see if they're the same. Our second metric is correctness, which measures if the student responded correctly to the tutor's previous turn, indicating the student's knowledge and question answering skills. We use prompting to identify if the student responded correctly or incorrectly, and measure if both the simulated and ground truth turn had the same correctness state. Our third metric is errors, which measures when students make an incorrect response to the tutor, what exact error did they make? This indicates students' particular misconceptions or knowledge gaps. We again use prompting to compare if the ground truth and simulated turn make the same exact error or both incorrect, making a different error. Our fourth metric is knowledge acquisition, which measures changes in the student's estimated knowledge state. This is quantified by anticipating future correctness using a language model that is trained on the correctness prediction objective. We bucket knowledge deltas and we compare the quantiles of the ground truth and simulated student turns using mean absolute error. Our fifth and sixth metrics focus on capturing the linguistic similarity between the simulated and ground truth student turn, capturing high-level features like length, grammar, and sentiment. We use two existing text similarity metrics, in particular the cosine similarity between sentence embeddings and the rouge L between the two turns. Our final metric measures how a student turn impacts the tutor's ground truth response, with the motivation that similar student turns will elicit similar tutor responses. We do this by measuring the perplexity of the ground truth tutor turn following the simulated student turn, and a lower perplexity indicates a more realistic student turn. We benchmark a variety of simulated student methods on our metrics, including various prompting methods, supervised fine-tuning, and a novel reinforcement learning method. Prompting methods involve writing an instruction that tells a pre-trained LLM how to act like a student, optionally giving some student-specific details such as a persona, and giving the context of the dialogue so far. The LLM then generates its best guess for how the student might respond at this point in the dialogue. In contrast, rather than relying on prompt engineering, supervised fine-tuning leverages student responses in a ground truth dataset to train an LLM to respond more like real students. Finally, we leverage reinforcement learning to encourage the LLM to generate more realistic student responses. We do this by first generating a set of candidate responses, evaluating them on all of our metrics, taking the average, and then forming preference pairs and training using direct preference optimization. As a result, the LLM's responses should be more aligned with the realism evaluation that we're using. We ground our evaluations on a publicly available dataset of real student tutor dialogues from the ED Learning platform. We benchmark a large set of simulated student methods, including supervised fine-tuning in DPO on the Llama 3, 3B, and AP sizes, as well as zero-shot prompting, ocean personas in context learning, and an Oracle persona using GPT 4.1 and using the reasoning model GPT-5 Mini. Our results show that fine-tuning works much better than prompting across most metrics, with 8B working slightly better than 3B and DPO working better than SFT. However, DPO's gains are modest, indicating that more advanced RL techniques are likely needed to get higher gains. Prompting works better on correctness, most likely because it tends to predict the students will answer correctly, which is the majority class, and the Oracle method copies exact errors from the given summary. However, across all methods, performance is quite low, indicating that more advanced simulated student techniques will be needed before simulated students can truly be reliable and useful for tutor training. We conduct a human evaluation with education experts to determine if our metrics are reliable. Annotators provide labels of correctness and acts on real and predicted student turns, and also compare the errors of these turns and the linguistic similarity across turns. The results of the human evaluation largely align with the results of the automated evaluation, with DPO performing much better than zero-shot prompting, but the Oracle method performing better on correctness and errors. We find a substantial agreement between human annotations and our metrics, as well as humans and our LLM annotations, as well as inter-rater reliability between the humans, showing that our metrics are highly reliable and aligned with educational experts. In future work, we hope to incorporate student learning histories, improve methods using RL, and expand to more domains like language learning and programming. Thank you all for listening, and find the links to our paper as well as our code containing our automated evaluations and simulated student methods.